Hi all, in this video let us learn about the topic polynomial curve fitting. Polynomial curve fitting. Let us consider a real valued input variable x and we are going to predict the real value target variable t, and this is generated from the function sine 2 pi x. So given x, we need to predict the value of the target variable t, and there are a total of say 10 data points given. Now these 10 data points are spaced uniformly in the range 0, 1 as shown in the graph, and the target dataset t was obtained by computing the corresponding values of the function sine 2 pi x. Now fit the data using the polynomial of the form y of x comma w is equal to w0 plus w1x plus w2x square. It goes on. So summation of wj x power j ranges from 0 to m. M represents the order of the polynomial, and this w0, 1, 2, wm, they are collectively denoted by the vector w. Functions such as a polynomial, which are linear in the unknown parameters, have important properties and are called linear models. Fit the data using the polynomial of this given form. Here, the values of the coefficients will be determined by fitting the polynomial to the training data. We have to minimize an error function that measures the misfit between this function for any given value of w and the training set. This curve fitting problem can be solved by choosing a value of w for which the error is as small as possible. Choosing order of the polynomial. Here m represents the order. Some sample graphs are shown here. Suppose if the order of the polynomial is 0, we could see it's a poor fitting. We are not able to fit all the data points. And when the order of m is 1, again, still it's a poor fitting and we are not able to fit the data points. It's again a poor representation. When the order of m is 3, it's the best fit. And when order of m is 9, it's again excellent fit. But here you could see the polynomial is passing through each of the point, and it's oscillating and finally ends up in overfitting. When m increases, the magnitude of the coefficients gets larger. When m is equal to 9, you could see the coefficients have become finely tuned by developing a large positive and negative values, but between the data points there are large oscillations like this. You could see the oscillations that are occurring when the order of the polynomial is 9. Here again, we could see the overfitting problem has become less severe when we are increasing the size of the data set. Here, the number of points is only 15, but here we have increased the number of points to 100. So thereby, this overfitting problem becomes less severe. The larger the data set, the more flexible the model as per the graph information we see here. In machine learning, this regularization is a technique which is generally used to prevent overfitting by adding some penalty to the loss function. And the modified error function is shown here. So in addition to it, we try to add some penalty to the loss function here. Now, we could see some graphs which are showing ln of lambda when it is minus 18 and ln of lambda when it is 0. So this plots of m equal to 9 polynomials which are fitted to the dataset using the regularized error function for the two values of the regularization parameter. You could see this table is showing the various values when ln of lambda is 0, minus 18 and minus infinity. So this shows that the model, how it works when there is no regularization. The impact of the regularization term on the generalization error you can see by plotting the values of the RMS error for both training and test set against ln of lambda. You could see the graph. You are plotting this RMS error against ln of lambda for both training and testing. And thereby we could infer that lambda is able to control the effective complexity of the model and hence it is determining the degree of overfitting. Thank you.